Well, I'm happy to be able to talk a little bit about the future, but as though I have a crystal ball, obviously there's many things of the future that I don't know and that none of us are aware of at this point. But by at least discussing some of these things, it will potentially bring about some ideas, some stimulating of thought, as well as at least sharing some thoughts of things that we're working on and looking into at this time. But in preparing to talk about the current status and the future, I thought, well, it might be good to do a little bit of independent review of what is going on in terms of the clinical studies that have been randomized. And so I looked through some of my literature and found 29 randomized or phase 3 clinical studies that I was looking at and wanted to kind of do a little quick review of those in terms of what complete responses have been reported, disease-free survival, overall survival, and even looking at reports of grade 3 or 4 toxicities. Not all of these articles reported all of these parameters, but I thought it would be interesting. This is a group of the published studies that I looked at. All of these were randomized claimed studies. And we don't need to review all of them, but a quick glance will at least refresh your minds to many of them that you've seen and are familiar with. In looking at these studies, I found most of them reported complete response rates with hyperthermia combined with radiation or chemotherapy. One was chemotherapy and radiation in one of these other categories. But it made a big graph, and I thought, well, maybe there's a good way of looking at this in a simple way. So of these 2,500 patients, I looked at the average percentage per patient that I put on the columns on the left so that you can see what the summary was, basically. So over on your left side there, seeing that about 60% of the overall review of these patients had complete response when hyperthermia was added in comparison to 42% per patient in these studies. Taking a look at what was being reported on these studies in terms of percentage of overall survival, the same type of thing was done where I found 2,300 patients were being evaluated in these studies with regards to overall survival, with 46% being shown for those receiving hyperthermia in combination with 38% reported per patient with chemotherapy, radiation, or both. The percent disease-free survival in these studies, again, not as many studies reported that, but those that were reported indicated in terms of the per patient average percentage of disease-free survival at various reported timeframes was 46% with hyperthermia added to either chemotherapy or radiation at 37% per patient. That was 924 patients that added up to that evaluation. In terms of toxicity, it was a little more difficult because a few of the good studies didn't really report something as a phase 3 or a grade 3 or a grade 4 toxicity, but those that did, I included in this little view. And again, out of 1,484 patients on the left, they're summarized to have 9% grade 3 or 4 toxicity when you added heat to either chemotherapy or radiation therapy, compared to 5% on the non-heated groups. Jumping into the current status of the current microwave hyperthermia systems, there's 2 systems mainly available commercially today, one being the BSD 500, a system on the left, and the other the ALBA system on the right. Different operating frequencies, but basically similar performance in terms of depth of penetration. The 500 actually has 8 microwave power channels in comparison to the single channel of the ALBA system. Each of the 8 channels can operate from 0 to 60 watts or can be combined into a single channel with 400 watt maximum. And the thermometry on the BSD 500 is a non-metallic temperature sensor, so there's no microwave interference or artifacts. This is because of the high resistance leads. So in that system, the power does not need to be turned off at the time that we make measurements of temperature, in contrast to the thermocouple uses where there's potential artifacts and interference that requires pulsing off of the RF. And also the 500 allows for interstitial capabilities as well as superficial capabilities to be combined with brachytherapy. I believe there's some intercavitary approaches with the ALBA system. Some of the future thoughts along the microwave development path is the potential of additional superficial arrays for dynamic control of surface temperature distributions, which would be possible with the multi-channel microwave system, improved water bolus interface options, as well as pre-treatment planning software tools that can be developed. Some are being worked on now, and more conformal patient interface devices. With greater implementation, I think that we'll be growing with the use of brachytherapy for our microwave interstitial techniques. There may be some intercavitary techniques as well that will fit in that. This is just an example of the 8 spiral array applicator that's been used here clinically in Europe at several centers. It provides for individual adaptation of the power in various areas of the treatment to provide more uniform heating or adapt the heating to avoid scar tissue. So that there's been 3 different sizes like that, 8, 5, and 3 centimeter spiral that's been provided for different treatment sites. A larger spiral has been used in a few centers. That's a 24 spiral. This is one in which the heating pattern on the right is shown, where we kind of can create both uniform distributions as well as control the temperature in different regions based on the temperature measurements on the surface or at depth. The lower left shows the current configuration of that system, where it's been packaged with a removable flap so that the cables are not really visible to the patient. That just I think we just started delivering those recently. So those are at least a few of the thoughts with the microwave system approaches and how they might evolve to some extent in the future. But I wanted to focus a little bit more in terms of the deep heating methods, RF capacitive heating, RF phased arrays, and maybe some comments about HIFU, although I won't get into HIFU very much. That's fairly new on the hyperthermia application methods. Some of the examples of some of the capacitive systems that are being used are shown here. You're familiar with the technical specifications of those. The one on the right, which is the RF8 system, they have much higher power levels than some because they include significant water cooling in the electrodes. This is because they observed substantial heating of the superficial fat when they were trying to heat at depth. That system had temperature sensors that could be used with the system to allow them to see what they were actually doing at depth. And because of that, they realized they needed more power and surface cooling of the fat. But other systems do not use cooling, they don't have as much power, and are somewhat limited in that respect. As mentioned, though, the capacitive heating techniques have been used for many years, started in about 1917 by Geyser and others, treating tumors of the body with RF techniques in the capacitive method, but it's been kind of reconditioned, just like the old-fashioned toasters do the same thing as modern toasters, but they work a little differently in terms of their dressing up and their functionality. Moving on to the RF phased array method, you're all probably familiar with that, but we surround the body portion with an array of antennas that radiate fields into the body. We use phase and power controls to steer the deep focal heating zones. Electric field is dominantly parallel to the body in this case to reduce heating to the fat and boost the central focus, in contrast to the current fields from electrodes that are perpendicular to the surface, resulting in the high fat heating that we're all aware of. This picture, I showed this yesterday, it's just an example of some of the different applicators with that BSD 2000 system. This shows the AMC systems that have been used treating patients with either the 4-ring or the 8 applicator ring configuration. This is a picture of the newer Alba 4D system. It also operates at the 70 megahertz fixed frequency rather than the variable frequency of the BSC 2000 system. It uses waveguides in 4 channels with 500 watts each with the metal thermocouples. We still are really awaiting independent clinical validation of this configuration. As we all know, whenever there's a change of configuration in a system in a major way, there requires clinical validation and evaluation. So the reliability and clinical utility are yet to be really established with this packaging configuration. But it uses the waveguide approach like we introduced back in 1981, but it has its own limitations. For example, it may not be adaptable to MR, non-invasive thermometry, which is an obvious thing. The deep heating numerical studies that we mentioned yesterday briefly, I'll get into more in detail later in this presentation, but just as a review for those that were not there, we used COMSOL 3D multiphysics modeling to model phantom cylinders that were filled with homogeneous phantom, either in a cylindrical form or elliptical form, filled with either saline or muscle dielectric material, and set with a 2/3 muscle connectivity with a 1 centimeter layer of superficial fat. So as a standardized type of phantom, it allowed us to compare the various heating techniques for deep heating, the arrays, the capacitive methods as well. And this is just the example of the 100 megahertz with a sigma 68 dipole configuration showing the selective large but centralized deep focus zone with that device. Same phantom with adapted conductivity parameters to match 75 megahertz showed a bit of a change where there was a little greater superficial fat heating occurring along the interface portions of the edges of the bolus. And that's because of quasi-static fields that occur there that begin to rotate. But a larger central heating focus as well because of the longer wavelength is seen. And we applied this, as I mentioned yesterday, to the AMC4 at 70 megahertz with their 40 centimeter long water bolus. We were surprised that we had as much predicted SAR heating in the fat surfaces near the bolus interface. There was nothing we did to the phantom any different than we were doing on the Sigma 60 except modeling the design of that waveguide design and its bolus structure. And that resulted both in the large central heating field, but a much lower SAR within the central area in that focus zone compared to the hot spot in the fat. The capacitive electrodes, we thought, well, let's apply the same technique and the same phantom to capacitive electrodes. Now, you'll notice that the electrode size we have, it was not quite as wide as the phantom, and that makes a big difference on the penetration because as you have an electrode diameter that's smaller than the width of the phantom or of the body, you'll have fringent fields. Those are represented on this diagram. And the result of this study showed that, yes, we had 100% heating on the fat layer compared to about 8% in the muscle phantom tissue right underneath that fat, and then dropping down to about 1% of the SAR of the fat in the central area. Now, to just explain what happens there in a simple way, it's due to the capacitive field divergent currents. And so think in your mind, if the RF currents diverge in the central region to a diameter of about 1.7 times the electrode diameter at depth, the expanding area at depth is the square of that diameter. That's the area of the energy, basically. So it goes up by a factor of 2.9 times larger area, which now dilutes the current fields across that dominant larger area. So the RF currents being that large underneath the fat layer, we can see that current squared times the resistance of the material is related to the SAR. That leads to this 1/8 drop in the SAR in the center of this example compared to the muscle SAR right underneath the fat due to the fringent fields. just to give you a basic, simple understanding of that mechanism and how the fringent fields change the depth. If we had a much larger electrode, we wouldn't have as much fringent field dropping it off. So for heating the central tumor, or for a possible non-thermal modulation effect, the RF power must reach the target area with an adequate level to be effective to do what we're trying to do. So it's important to keep in mind these fringent fields. Now there's something that we sometimes also do not think about when we think about these capacitive electrodes, and that is the visceral fat. Many patients will contain visceral fat. And RF currents from capacitive electrodes will only converge if bone, fat, or air regions divert these currents to concentrate them in certain areas that, of course, are not under an operator's control. They're part of the patient. But, of course, bone and these other structures can alter the current flow paths of RF currents. So it's not good enough, even with the capacitive electrodes, to measure a high temperature in one part of the tumor unless you understand how these low dielectric structures might be diverting currents into certain sections, because you might be missing the rest of the tumor with these currents. So the visceral fat distribution is unique to patients and limits any consistent deep heating results, I believe, from the capacitive electrode technique in patients that happen to have visceral fat problems. Bone structures is kind of common between people, but the visceral fat might be a little different. Anyway, there's a limited future, I believe, for capacitive electrodes in deep heating because of the superficial fat layer absorption issue, the field shape that's divergent with a lack of control, the RF current flow paths that are altered by visceral fat as well as bone structures and air underneath the superficial layer, and it's not compatible with imaging-guided SAR steering, such as the MR-guided techniques that we're looking for. And going back to some old terms that used to be used in the early days of deep heating, it's a form of dump and pray for an RF conductive path to reach the tumor somehow. Okay, let's jump over to the phased array approach. You've seen these pictures before, the BSD 2000 system. As a review of those that didn't see this yesterday, we started working with the MR integration back in 1997 in Munich with a 0.2 Tesla system for feasibility. This later, in a collaborative development with Peter Wust and others at his center, we developed the first 1.5 Tesla integrated system for deep hyperthermia in Berlin. That system was a model for what was delivered later with the Siemens Symphony at Erlangen, Dusseldorf, as well as Tübingen. But before that, we actually configured a research system at Duke to work with the GE system that was on a mobile cart. That was not used clinically, but it was a research system, and of course then the Tübingen system, similar to the others with the Siemens Symphony. The Rotterdam system was now integrated as well with the GE 450W and is in clinical use. And the newest system is one that was going through quite a change. One thing was, as we looked at all these different MR configurations, we realized every time we had another MR configuration, there was something that was going to be changing significantly, causing us to redesign the patient handling structures. And it was decided that we needed to have a configuration of the system that could adapt to the standard diagnostic tables used for MR. Some of those are portable carts, others are fixed, but in that way we replaced the sling with patient pads. And these pads in the applicator configuration allowed us to actually have the water bolus underneath the patient, who's elevated by these pads, and the applicator would open, providing for easy access. So far, they tell me they've treated about 120 sessions with that system, if I remember right. So it's in clinical use, being validated in clinical use, and that's important as we go through each of these iterations of the system development. This year, some of the new developments that we're in process and working on is a new water system for our MR configurations that might also apply to other configurations of the 2000 system. We have software controls for the universal system that provides complete software control of this water handling system for these phased arrays. Also, we're looking at a redesign, replacing the old rack of the computer with a simple little tabletop interface card or board that would be underneath the monitor, that would be an all-in-one computer monitor, where the computer is actually in the monitor itself rather than in a separate compartment and chassis. And so that's being worked on. Now this water system is one in which you think, well, a water system, how it can be special about a water system? But it has its own built-in chiller. It has improved air removal, pressure handling and monitoring, where we can monitor the pressure and the lines, leak cache tubs, leak detection, onboard chillers, as I mentioned, so that we don't need to use the hospital chilled water for handling substantial chilling of the water. Sensors, in addition, that we haven't even thought how we're going to use some of these sensors, but that might even lead to automatic fill and drain capabilities and capacities, the potential of automatic bolus air removal. Additional feature is pedestal LED water flow indicators that are next to the MR itself. Addition of system control function and buttons on the electrical control box for quick troubleshooting. No need for deionized water filters because we have a closed system with this system, using 3 separate water level controls that communicate to the operator through this smart controller. Added ability to drain and refill from the pedestal, as well as adjustable chilled water source temperature for patient comfort and circulation. The software has been modified so that to work with this system, even when we're not doing a treatment, the computer is in control of the water and the cooling taking place in that system, as shown in that little circle underneath, where it actually would be showing to the operator the temperature that's been set for the water system and the temperature that's actually residing in the chamber that we'll use to fill the patient. During a treatment, this new control screen is provided where we have the ability to set by the operator during the treatment or change the chilled water supply. We will be displaying at the side of that the measured chilled water supply so they can see this control loop and the response to that. We can establish and have the operator in control of a circulation time, where between MR scans, this circulation time can automatically just be triggered and set, and last 2 minutes, turn off, settle the water so we'd be ready for the next MR scan. And a selectable settling time as well that we would have for the water, where it would trigger the operator that it would not be time to do an MR scan until that resettling time has been completed. Another thing that I'll be talking about a little bit later this afternoon is the non-invasive brain array we call the Hal.o, that's operating at the 915. We're currently using the BSD 500 as the test vehicle for that, and so far we're finding that it works quite well in providing this particular antenna array. We have 72 dipoles in this array. It's constructed with 24 in each of the 3 rings, as shown there on the left, and we've been testing this in phantoms. I'll be reporting more about this later in the afternoon, as I mentioned, but we'll give you a snapshot of some of this information where we're looking at the capability with numerical modeling to steer within the human brain, where we use the COMSOL multi-physics model with blood flow, perfusion, as well as various characteristics of the head to model the temperature distribution that we'll achieve within various targeted positions in the brain. This particular slide shows that we were comparing different numbers of channel. Where we have 72 antennas, what if we have an amplifier for every dipole that we have control of? Well, we find that that's not any better than having a channel of microwave power supplying a group of 3 antennas. You having a 24-channel system, we have basically the same result. We do see some degradation when we go to the 8 amplifier channel, where a single amplifier would operate 9 dipoles. However, this particular optimization, and most of that we've done, is simply optimization of phase steering and not amplitude steering. I'll be showing some examples of what you can achieve by adding additional optimization of amplitude steering in the afternoon. But jumping quickly to some of the results I'll show later, we've done simulations not only with our numerical modeling, but we were able to facilitate work at the Air Lincoln University Center using their 3D MR system to measure temperature in phantoms that we were using to heat with this brain array. As shown on the left is the image obtained through the Sigma Vision program, showing the size after about a 3-minute heat-up period. On the right is the numerically modeled results of that same test, showing very good agreement between the two. Part of this was to determine steering capabilities. One of the ways to steer within a phantom like this would be to change the physical position of the phantom within the aperture and keep the phases all focused at the center. And so you can see on the left, when we lifted the phantom up, heated up, the focus remained centered in the array, but moved within the phantom, which would be the same thing if we displaced the head. And the numerical modeling on the right shows a similar result with good comparison. This shows an example of doing electronic phase steering, where instead of moving the head, the head phantom was remaining in the center. We shifted the phase to move it by 18 millimeters to the left. So on the left, we see the top image is what we saw with the MRI, and the bottom was what was being predicted by the numerical model. On the right, it shows the configuration of this, where we would drive each of these channels with different phase leads, and that would create this phase shift that we're talking about and showing on the left. So there'll be more about that this afternoon, but talking about some of the new deep heating practices that we envision being implemented in clinical use that we're starting to describe and talk about is using possibly non-centered phantom for phase steering in the deep phased arrays. If a patient has discomfort with water bolus pressure on the anterior surface, they can lift the patient, maybe 2-3 centimeters, and just alter the steering to compensate. Superficial heating with power controls is another area that has not been used very much with these systems, but it's a very flexible system, as well as the future MR image guided treatment optimization. An example using the lamp phantom on the left, lower you'll see here is a case where we have a centered phantom, but we've caused a 0-3 steering, which moves it towards the anterior 3 centimeters, and what that focus is. But if I was to lift the phantom 2 centimeters above center, as shown above that, all I'd really have to do is set the phase target at 0 and 5, and I result in the same heating pattern. Similarly, on the right, the example of the lamp pattern, and of course this is all just with phase steering. We've not adjusted the power levels, but if I was to want to have a -3 steering on a centered pattern that would be instead be offsetting with the patient, I lift the patient up 2 centimeters, I choose the Y number at a -1, I get the same focus in the patient. That might be something useful in clinical applications. This just demonstrates also, using the Sigma Hyperplan, how we could use superficial control of the heating pattern by using 1 or 2 power channels only, where we don't operate the full channel, but we want to just do superficial heating over a large area near the superficial region, extending down maybe 4 or 5 centimeters. And just shows different examples of moving that superficial heating zone around the side of a patient anatomy with the Sigma Hyperplan program. One thing I wanted to talk about briefly is when we start envisioning doing things in the future, new developments and new ideas, it's important to understand, I believe, the characteristics of the cells and the dielectric and conductivities related to this, where future developments need to understand that there's frequency dependence of the field interaction caused by the cell wall membrane. Between the frequencies of about 0.1 to 100 megahertz, RF currents will tend to flow around the cell because of the capacitive barrier of the drier cell membrane. Once you get above the 100 megahertz region, those currents begin to flow more and more within the cell, going through the membrane by overcoming the capacitive barrier. And it's important to at least get an idea of these things. This comes from some of the studies of Pethig, The diagrams that show this effect on the curve that's at the top coming down starts at 10,000. That's the permittivity of tissue. The conductivity is the other curve starting at the bottom, showing that as we go up in frequency, the permittivity of tissue drops substantially. That's because of the cell wall capacitance and its membrane effect. And you can see that that's changing all the way down until you get down close to and a little beyond the 100 megahertz region. And that's showing the transition zone where the RF currents will be flowing through the cell more than they'll be flowing around the cell. It's also interesting to see that the conductivity curve remains quite flat and just very gradually is increasing in tissue until you get up to about 1,000 megahertz. That's because at that frequency you have the water resonance mechanism becoming more dominant and the power absorption, where below that area you have more the power absorption being the ionic heating of the tissues. And this is explained in Pethek's book and his other publications. But so as we think about those things, keep those in mind as we look for future advancement developments. Now, moving on to the numerical advanced study, when we were evaluating where to go in the future with phased arrays, with these 3D multi-physics models, again, the same type of model I described, we ran more than 300 solutions with different variations in the design and the configuration and frequencies. I know we spent some time with Gerard Van Roon kicking through some of those figures in an afternoon, I think. But just to give you an idea as to what can be possible is that on the left you'll see a sigma 60 type of shell, water bolus, but it has 24 dipoles like the sigma I, okay? But it's operated at 250 megahertz. In this particular case, we use the bolus with a dielectric of propylene glycol, which is a little bit lower dielectric constant. We found that we could have a predicted focal volume of about 200 cc of tissue for the 50% SAR in that central focus region. Compared with, on the right, at 100 megahertz, it was almost 2,000 cc. Now, there's times where we would like to still have 2,000 cc for large tumors, but there's also times where it might be beneficial to have a more focused deep heating pattern as well. Emphasize that whenever you have that smaller focus, even more should we consider non-invasive thermometry as a need to guide and measure where we're heating. Another continued example would be the steering of the 250, where we've got the same pattern on the left, but on the right we use phase steering to steer about 4 centimeters to the right, and showing that we maintain still a fairly good, sharp focus in that region that can be phase steered. We looked at all kinds of different steering patterns like this. Another example of the 250 megahertz is shown here with now an elliptical shaped phantom, more body-like rather than the round phantom, showing similar results, different characteristics a little bit, but still fairly small heating volumes. About 175 was the 50% primary focus in the body at the deep side, as well as we would steer this around. We've looked at other frequencies all the way from 434 down to the 100 megahertz. An example would be we looked at 175 megahertz. The 3D optimization of phase with these same 24 channels, you can see on the left, still had a central focus. We were starting to pick up some superficial heating near the surface in this particular case. The volume in the center was about 334 cc's. Here we took the shape of the sigma I applicator with the 24 dipoles that we have been using basically, and ran that at 175 megahertz just to see what would happen. And again, we have a smaller focus than we normally have, but still have steering capabilities. This is another case of steering off to the side with the 175 megahertz 24 channel configuration, but again showing an example in a sigma I form. Well, okay, with numerical modeling you can run a lot of tests and learn a lot of things. I'm just showing you some examples of those things that might be possible as we move forward. This is just an example of 140 megahertz with a water bolus, still with a fairly large focal region, almost 1800 cc because of that larger wavelength. The size of the focus is directly related to the wavelength in the tissue. Jumping back to 250, another example was here, instead of an eye-shaped applicator, we thought, well, let's make an elliptical shaped applicator and look and see what that looks like with an elliptical phantom. And so we still had a very small central focus in this example of 143 cc. We were starting to see some superficial hotspots picking up, as shown at this frequency, and that could be controlled by doing some additional things. I won't get into the details of that, but just showing you some of the examples of these things that would be possible. Again, like yesterday, just to review, there is a role potentially for not only the high RF and the HIFU phased array approaches with hyperthermia, but keep in mind, even at these higher frequencies that we're going to, the focal volume is much larger than what you'd be having with a HIFU system that would need to have rapid scanning. And so I feel there's potential for both capabilities. On this chart we show sort of the advantage of each and the characteristics of each. So kind of in summary, the future clinical applications, we think as these technologies evolve and clinical applications evolve, yes, there's going to be opportunities to expand to proton therapy with hyperthermia, which will potentially mimic the carbon ion treatments. I think that there's going to be a renewed interest in the potential of using brachytherapy with hyperthermia and interstitial techniques, like has been reported here, and we have growth in that happening even in the United States right now. That's one area where the 915 megahertz system comes into unique benefit, because of the smaller wavelength size helps us to control the heating pattern better along the long inserted direction of the interstitial antennas. There's immune response with hyperthermia that's going to be a growing topic. Excuse me. The brain targeted phased array treatments. We certainly see the superficial arrays with more uniform heating capability. And then some of the tools that are being developed, and there's probably many others, but the brain phased array, the Hal.o Advanced high frequency phased arrays that will probably be integrated in a multi-frequency configuration where we have both large heating volumes as well as more focused heating volumes. MR guided focused thermal therapy with the superficial arrays as well. Certainly further evolution of the current systems, which we've continued to do for the last 40 years. Evolving those, modernizing them, and providing more tools along with them, and advanced treatment planning techniques as well, which we believe is quite important. So I thank you for your attention and sharing your lunch with me, and hopefully if there's any questions we can talk about them, but appreciate your attendance today. Thank you.